No, it's not recording. Yeah, thanks. Okay. Right, then I've got my bulb there. Right. Right, so that's the setup that I have. So I've got the bulbs there. So I'm just going to check. I'm just going to change the resistance here so that it matches. So here's 10. I'm just going to make it a 5. Right, I make them to have the same resistance. I make them to have the same resistance. Make them 5. Right, so I've got 5. Then my battery there, my
Yeah.
voltage is 9 volts. Okay. Right, then I close my switch.
Thanks.
Right,
Because
so the current is kind of slow here. Maybe my resistance, let me just increase the voltage, maybe make it 12. Make the voltage 12. Okay, it's a bit better. So it means the resistance is quite high. But basically, you can see what is happening here. Your current is going to flow through the bulb. When it gets here, it splits into 2, right? Because of the parallel resistors. So the bulb, these 2 bulbs here, they're in parallel connection, and that one is in series with the battery. And you can see the resistance there. The resistance here it's higher. Sorry, the brightness here. This bulb is brighter than these other ones here. You can see with the intensity of those lines and colors there. Right. So why is it higher here? It's because this side there's more current flowing here. If we can put an ammeter here, we're going to see that the current here is higher. And when the current comes here, it's going to split. So for example, if I put the current here, if I can just put an ammeter here, let me just put an ammeter. If I can put an ammeter to measure this, right? The current that is flowing in the outer channel here, right? In this channel before splitting, you can see there it's 1.6 amperes. So when it gets here, since they've got the same resistance, then it means current is going to split into half. So this side is going to get 0.8, and this other one here is going to get 0.8. We can verify that and just measure it using that ammeter again. All right, we put an ammeter there. Right, there it is. So you're going to get 0.8 amperes. So when current comes here, it splits into 2. You've got your 0.8 and you get your 0.8. So it means resistors that are in parallel, they are current dividers. Right, let's check the voltage. What's going to happen with the voltage? If we bring the voltage here, just measure across the battery, right? The voltage across the battery is 12 volts, right? Then we measure the voltage across the voltage on the bulb in parallel. We are getting 3.99, which is roughly 4. So this one is getting 4, and we know resistors that are in parallel, they get the same voltage. So let's verify that and see what voltage we're gonna get here. On the other bulb, we're also getting 3.999 volts. When we round off, that becomes a 4. So these 2 bulbs that are in parallel, they get the same voltage. So the battery here has got a 12, and these ones are getting a 4. So it means the bulb that is in series is going to get 12 from the battery minus the voltage on the parallel. 12 minus 4 is going to give you 8. All right, so this one must give us a reading around about 8. Let's verify that. So we put that. Right, we're getting 7.998, which when you round off, it gives you 8. So it's going to be 8 plus 4 to give you 12 across the battery. So resistors that are in parallel, they get the same voltage, but they split the current. So resistors in parallel are current dividers. because the current splits, but the voltage remains the same. And resistors that are in series, they are potential dividers, and they get the same current. So this one, the one in series, and the other one, this one and those ones here, they are in series with each other. So they are splitting the voltage that is coming from the battery into two, right? But not equally, because the arrangement is different. These two have got lesser resistance here, right? So they will get lesser voltage. So here, this one has got more resistance, so it will get more voltage. That's why here we are getting 8, and here we are getting a 4. So 8 plus 4 in the parallel gives us the voltage across the battery, which is a 12. Is that clear?
Yes.
Right. So that's what we have for resistors that are in parallel. When we have got a combination of you've got a combination of series and parallel. So you can have even another bulb here in parallel, so that this one is going to have two bulbs in within the parallel. They're going to be in series. But we'll look at some examples, and we'll highlight all those particular points. Right. So I'll move on to a question. I'm going to take out a question from a past paper, then we look at that. So let's do that. Okay. But before I do that, I'm just going to look at an example from Siavula. Right, I explain one or two things before we proceed. Right, so let's look at this one. We've got question example 10. Right, you've got to consider the circuit diagram. You've got your 7 volts is the battery. You've got another resistor there is taking 4 volts. This one is taking 1 volt, and the voltage across the parallel is not given. Then the question says, what is the voltage across the parallel resistor combination in the circuit shown? Hint, the rest of the circuit is the same as the previous problem. Right, we did look at the previous problem, but we'll just continue from this one here. So step number 1, the circuit is the same as the previous example. Let's just check what is happening in the previous example here. It's those 3 that are in series. So that's what we have. Okay, right. Then the difference, the voltage difference between the 2 points in the circuit does not depend on what is between them. So the answer is the same as the voltage in parallel, which is 2 volts. How do we get that 2 volts? Basically, what we are saying is these two resistors are in series. All right, they're in series here with the battery, and when it gets here, these 3 here, they're in parallel with each other, but they're in series with the 4. All right, because it's just 1 1 1, so it basically is 3, just like the other example that you saw on top. So basically, when you want the voltage on the parallel, what you're going to do, you're going to add these 2 here, 4 plus 1 to give you 5. All right, then we know the voltage that is on the parallel is the same for all 3 resistors. So the voltage that is flowing in the parallel, if we add it, the answer must be 7. So we're just going to say 7 minus the sum of the 2, 4 plus 1, which is 5. So it's going to be 7 minus 5 to give us 2. So the voltage across here is a 2 volts. All right, so that's our answer. So this one gets 2 volts, this one gets 2 volts, this one gets 2 volts. Resistors in parallel, they get the same voltage. Right. Resistors in parallel are current dividers, therefore voltage remains the same. Right. So we have a circuit with a battery with 5 resistors. Here they're just explaining now. So this is what I've explained. You add the ones that are in series, 1 plus 4, then you get a 5, then you subtract. So V battery is equal to V total. So V parallel plus V unknown, that must give us the total. So you subtract the 7 minus the 5, then that will give you the 2. So that's what we have there. So here is just an explanation, but it's a bit long, but the concept is the one that I've explained. Right, so that's what we have there. So let's have a look at past paper. We see how we can solve this. Okay, I opened a couple of questions here. Okay, let me just close this. This is the 2019 paper that was written last year in November. All right, so let's see if we can get a multiple choice. Okay. So here we have 1.10, multiple choice. The maximum work done per unit charge by a battery is you've got EMF, you've got current, you've got resistance, and you've got terminal voltage, terminal potential difference. So they say maximum work done per unit charge. Work done per unit charge, we know what is this. This is your W over Q. And we said W over Q. If I can just share this. Let me just open where I can write. Okay. From what we've seen, we saw that work done over unit charge. So that becomes over Q. So work done over Q, what does it give us?
C.
Work done per unit charge. Kulufelo, what do we get? Kulufelo? What do we get?
Volts.
We get volts, yes, Joshua. Right, so you get your voltage. So voltage is equal to work done per unit charge, right? So that's your V. So it means the answer that we are talking about is about V. It's about voltage. And voltage is divided into two. We have got your EMF, you've got your EMF, and you've got your terminal voltage, right? Depending with how you measure it, right? So here you're going to have your terminal voltage. Terminal voltage. EMF is the voltage that is measured when no current is flowing. And terminal voltage is when the voltage that is measured across the battery when current is flowing, right? So now we need maximum. So you can only get maximum energy if no current is flowing. So it means this one is out. Terminal voltage is out. And your answer must be EMF because they said maximum. You can only get maximum if no current is flowing. So the answer there must be EMF. So let's check the answer. Right, so here back at this one, the maximum work done per unit charge, we know it's a potential difference. So you eliminate the wrong answers. Your answer must have to do with the voltage. So A is a contender here and D is a contender. B and C are out because they are not talking about work per unit charge, which is voltage. So your answer is either A or D, right? Because of maximum, it means no current is flowing. So it means the battery is giving maximum energy, right? So the answer must be EMF. So the answer there is A. Right, then we move on to the next one. We look at what type of questions they got from this paper here. It's electricity. It's normally the last one on your paper one. It's normally the last question. Right, question number 11. So it says in the circuit diagram below, the resistance of the battery, ammeter, and connecting wires are negligible. Why are they negligible? It's because if their resistance is high, then it's going to affect the current that is flowing here. So it will affect the reading on this ammeter here, all right? So they will increase the resistance of this particular circuit. Right, so we move on. So we assume they've got negligible resistance or zero resistance. Right, 11.1, explain the meaning of the following: a current of 5 amperes. Current of 5 amperes. What does that mean? Current of 5 amperes. What does that mean? For 2 marks.
The movement or the force of charge moving through the circuit is measured at 5 amps.
It's 5 amps. Okay, not exactly force, but let's have a look. Let's look at the formula first. First, you need to understand what are we talking about. We're talking about current. And what is the formula for current? Current, we said from the formula, you normally get it as Q is equal to I T, where Q is charge, I is your current, T is your time. So we are given current, so we need to make I the subject. So we're gonna divide this side by T, divide here by T, your time. Sometimes you find the delta T here, change in time, right? So your current is equal to Q over delta T. So what does that mean now? We are given 5 amperes. We're given 5 amperes. What does that imply? It implies that if we have got 5 amperes, obviously when you divide, you want to make your denominator 1. So it means here we're going to have 1. And what are the units for time? Units for time are going to be seconds. So it's going to be 1 second. So Q is our charge. So for us to get a 5, it means the numerator must be a 5. So it's going to be 5 C. This is what it means. So 5 amperes means 5 coulomb of charge flow per second. That's what it means. 5 coulombs of charge flow per second. Are you following?
Yes.
Yeah.
Yes. So 5 amperes means 5 coulomb of charge per second past a given point. Or the rate of flow of charge is 5 coulombs per second. Or 5 coulombs of charge flow per second. That's what 5 amperes mean. If I've got 20 amperes, it means 20 coulombs of charge. 20 coulombs of charge flow per second. From the formula, where am I getting all of this? I'm getting it from here. Q divided by delta T. So it's charge per unit time. That's what we have. Okay, so that's the explanation for that one for 2 marks. So 5 amperes means 5 coulomb of charge flow in a second or per second. Right, let's move on to the next one. Opening my question again. Right, we move on. It says, calculate the effective resistance of the parallel resistors. Effective resistance. What do we mean by effective resistance? It's like if I'm to remove this 4 and the 6 and replace them with one resistor of equivalent resistance, how big should that resistor be to have the same effect as a 4 and the 6 connected in parallel? Right?
10.
Come again?
10.
10. Right. No, it's not 10 because they're in parallel. Remember, how do you add resistors in parallel?
Oh, 1
5.
1 over. 1 over. And remember what I said. What did I say? I say when you have got resistors that are in parallel, if you add them, the answer must be smaller than the smallest resistor.
It's 5, sir.
It can't be 5. The answer must be less than 4 because the smallest resistor is 4. Are you following? Kulufelo?
Sir.
Are you following? It can't be 5.
Yes.
Okay, let me do it. Let me do the calculation. Right, if you go to your formula, what does the formula say? The formula says 1 over R parallel is equal to 1 over R1 plus 1 over R2. That's the formula for adding resistors that are in parallel. Therefore, here we're going to say 1 over 4 plus 1 over 6. 1 over 6. Are you following? It's equal to, then I'm going to look for a LCD here. I look for a number where 4 and 6 can go into. The answer here is going to be 12. 4 into 12 goes how many times? Goes 3 times. 3 times 1, I get a 3. You can use your calculator for you to calculate this. 6 into 12 goes 2 times. 2 times 1 gives you a 2. All right?
12.
Right. So your answer is 5 over 12. But 5 over 12 is not your final answer because remember our R parallel is a denominator. We need to flip this. So you're going to have to flip. So your answer here that I'm getting is 5 over 12. Then I'm going to flip it. I need R parallel. I don't need 1 over. So I'm going to flip also the answer here is going to be 12 over 5. I flip this. What you do to the left, you also do it to the right. It's going to be equal to, I say it's 5.
2,4.
Come again, 5 into 12, I get 2. Remember 4 is 2,8. Am I right?
No, sir.
No.
2.4.
2,4.
2,4. Okay. All right, 2,4. Yes. Okay. All right, so my answer here becomes 2,4 ohms. So when I have a 4 resistor connected in parallel to a 6 ohm resistor in parallel, the sum of the two is going to give me the smallest, the answer must be smaller than the smallest resistor. So here, this was a 6. So my answer must be less than 4. That's why my answer is 2,4. So when you've got resistors in parallel, when you add them, your answer is going to be smaller than the smallest resistor. So if I had another resistor here, that is maybe 1 ohm. If I connect a third resistor to this circuit here, 1 ohm, right? My answer here is going to be less than 1. It's going to be 0, something. Because when you add resistors in parallel, the answer must always be smaller than the smallest resistor. Are we clear now, Joshua and Kulufelo?
Yes, sir.
Yes. So please don't confuse series and parallel. Joshua, you said 6 plus 4 because you just added like that. Parallel, you must use the formula 1 over R1 plus 1 over R2. Clear?
Yes, sir.
Right. Okay. Right. We move on to the next question. So here we've got our resistance here 2,4. We move on to the next question. Right. The next question says, which one of the voltmeters V1 or V2 will show a reading if the switch is open? If the switch is open. So let's go to the 2 and check which one is going to show a reading. We've got V1 across the battery. We've got V1 across the resistors. Which one is going to show a reading here? V1 or V2?
V1.
V1.
V2.
V1.
Ah,
V2.
sir.
Huh? You're saying V2?
Why V1? Why V1, sir?
Joshua, why do you say V1?
It's a closed circuit, whereas the statement says that the switch is open, therefore there's no current flowing through the circuit. So whereas the voltmeter is connected in parallel to the battery where there's no opening.
Okay. So basically our battery is the one that supplies energy. All right. So between
Yes.
the two spots here, there's a potential difference here. And here, no current is going this way. So there's no energy being supplied to the outer circuit here. So that's why V2 won't have a reading because there's no energy that is coming to the resistors. But here, the battery is supplying energy here. So we'll get a reading here. So V1, yes, it will give us a reading. V2 won't give us a reading. Why? Because source of energy is the battery. No current can flow if there's no energy. So here there's no energy coming through here. But here the battery has got energy here. So something will happen here. Clear?
Okay, sir.
Yes. So the answer is V1. Okay. Next one says switch S is now closed. So we now close the switch here. Right. Then it says, how does the reading on voltmeter V2 compare to that on V1? Choose from higher than, smaller than, or equal to. So we go to the diagram. We are closing the switch, all right? We need to know which one will have higher energy. Is it higher energy? Oh no, it's the reading. How does the reading on voltmeter V2 compare to that on V1? V2 compared to V1, all right? How does V2 compare to V1? What's your answer? Is it greater than, smaller than, or equal to?
Smaller.
Smaller than.
Smaller than. Why smaller than?
Because it passes through a resistor.
It passes through a resistor. Which one?
There's 3.
There's a resistor there. So
there's one resistor connected in series, whereas two are connected in parallel.
Yes.
Therefore, what is the one in parallel has less voltage than one in series?
Okay. Why? Why is it like that?
Because what is the resistors in parallel are current dividers.
Yes. Okay. Resistors. So here you're not gonna say current dividers. You know, you have, because we're talking about voltage. You're supposed to say resistors in series are potential dividers. So the voltage that is coming from the battery, the R is gonna take some of the voltage. Whatever is remaining, it will go to the 4 and the 6. 4 and 6, since they're in parallel, they get the same voltage. Example, let's say the battery was 10, right? Then let's say R takes 3 volts. So it means 10 minus 3. It means the resistors that are in parallel will get 7, because these two and the R, they're in series with one another. So basically what is going to happen, the voltage across the V2 plus the voltage of R will give us a total across the battery. So it's because resistors in series are potential dividers. That's why. So if it's 10, this one takes 3, this one will get 7, and 7 is less than 10, the total. So for us to get V1, we have to add the voltage across R, and we must add the voltage across the parallel for us to get V1. Is that clear?
Yes.
Right. So your answer there is smaller than. Remember, you're comparing V2 to V1, not V1 to V2. You must understand the question. How does the reading on voltmeter V2 compare to that on V1? The answer is smaller than. If you look at V1 comparing to V2, then your answer must be higher than. So you must be careful here. Which one is your reference one? Right, next one, 11.5. Calculate the current in the circuit if 0.3 coulomb charges pass through the ammeter in 2 seconds. Once again, they are giving us a year. Here's our ammeter. So we need to calculate the current, and we are given charge, and we are given time in seconds. It takes us back again to that calculation that we did earlier on, where we had Q, that calculation that we had there, this one here, where we said current is equal to charge per unit time. So we are told here, what are we told in this question here? We've got 0.5, if I'm not mistaken, they said 0.5, am I right?
0.3.
0.3, okay, let me just do it again here. So it means 0.3 divided by 2 seconds. And this, where is this one coming from? It's coming from Q divided by time, which is going to give us current. So this will give us I, current. So you simply divide those two, then you get your answer. Is that clear? Your answer maybe will be 0.15. Right, 15 amperes. That becomes your answer. Right. So you're going to get your marks for doing that. Okay. We move on to the next one. The next one says, 11.6, the potential difference across resistor R is 5 volts when the charge of 0.3 flows through it. Calculate the energy transferred in resistor R. Calculate the energy transferred in resistor R. You look at your marks. How many marks? You've got 3 marks. So what are you going to do? It means just formula, substitution, and answer. So you do your data here. What are we given about R? We have the voltage. What else are we given? We are given the current. We're given the, sorry, not current, we're given the charge C. Right? What are we looking for? We are looking for energy. Which formula connects voltage to charge and energy? Energy transferred, remember, it's work done. Remember this. Right, so we're going to go back to our answer then. We have from the formulas that we looked at earlier on, we looked at this formula here. V is equal to W over Q. So voltage we are given as 5. Charge we are given as 0.3. Now you can find your W. So what we're going to say, we're going to say V is equal to work done, or you can even make it energy. It's also acceptable. Energy over Q. Why? Because energy and work done, they're all measured in joules. They're all the same. When you're doing work, you're transferring energy, right? So this is equivalent to work done over Q, right? Then you substitute your V. Your V is your 5 volts, is equal to, right? You can leave out the units here so that you don't get confused. All right, let me just change the pen here. All right, so you're going to have your 5 is equal to your energy or your work done over your charge. Your charge is 0.3. Then you cross multiply. This is over 1. So those are the marks. So mark for formula, mark for substitution, and you cross multiply. Your energy is going to be equal to 0.3 multiplied by 5. Then you get your answer. All right. You get your answer there, which is going to be 1.5, if I'm not mistaken, 1.5. Right? Am I right?
Yes, sir.
Right, you get your joules. Your answer must be joules here because the energy is measured in joules. So your answer becomes 1.5 joules. Clear? Right.
Yes.
So this is how this question is supposed to be attempted. This is how you answer this question here for 13 marks. That's what you get. Right, then that was 2019. I think that was an easy question. We've got about 4 minutes, 40 seconds left. Let's just look at 2018. All right, 2018, what do we have? Let's just look at one multiple choice. Did I skip it? Yeah. Looks like there's no electricity question here. Okay, there it is here. Okay, 2 identical light bulbs are connected in parallel as shown in the circuit below. Right, voltmeter V1, V2 are connected across each light bulb. So they say 2 identical. What do you understand by identical light bulbs there?
Have same resistance.
They have same resistance, so they've got the same resistance, these 2. Which one of the following voltmeter readings is correct? Which one of the following voltmeter readings is correct? So there you have it. All right, yeah. So first one says V1 and V2 are the same. Next one says V1 is 2 times V2. V1 is half V2, and V1 is a quarter V2. Which one of the following voltmeter readings are correct? So from what we've learned, what do we say? What's the answer here?
A.
Answer is A, correct. Why? It's because the resistors that are in parallel, all right, they are current dividers. Therefore, the potential difference remains the same. So the reading on the, because here there's no resistor that is aside here, which is in series. Both of them are parallel with the battery. So it means the voltmeter reading of the across the battery is the same as V1, which is the same as V2. So your V1 is the same as V2. So the answer is A. The rest, they are not correct. Right, then we move on to the last question, normally of paper 1. Right, we only have about 2 minutes, 40 seconds. Okay, let's just quickly see what we can do. Consider the circuit diagram below. So you're given there 24 volts, all right? You guys, you must know the difference between a cell and a battery. A battery is made up of many cells. So this is a battery, 24 volts. Right, so we've got a voltmeter, we've got another bulb, 8 ohms, we've got 2 8 ohm resistors in parallel, we have ammeter readings, we've got a switch. Right, a switch S is open, so the switch is open. Write down the reading on voltmeter V1. So V1, what is the reading here?
24 volts.
24 volts, because no current is flowing. So what the battery has is what is going to be read by the voltmeter across it here. So it's 24 volts, correct? Next one,
Yes.
ammeter A1. What is the reading on ammeter A1?
Oh.
I is equal to 2.
It's 1 mark, so you don't stress. It's 1 mark. And you must look at the
24.
switch. The switch, when the switch is open, what does that mean?
No charge.
It
So
means no
0.
current is flowing. No current is flowing, yeah. So the reading on the ammeter would be
0.
0 amperes. So please don't just write your answer 0. You must also include the units 0 amperes, no ampere. Why? Because the switch is open. Yes?
But you said it's 1 mark, so we don't have to stress.
No, but remember the all values must go with units. By stressing, I mean you don't have to do calculations here. Just a straightforward answer. Yes, you just check the switch is open, then it's 1 ampere. All right, I'm gonna put this as your activity, then you finish it up. Now our time is up. I've got, I think, 30 seconds left. So these are the kind of questions that you get under electricity. So basically, we are done with term 2's work. This is the last topic for term 2. So now we're going to be doing some revision on electricity and all other questions. Then we take it from there. Right? Any questions?
No, sir.
All right. So let's meet on Wednesday at 2 o'clock. Please tell the others, Jolisha and them.